All right, hello there. Looking at the chain rule today, just an introduction. We got a couple of videos that we're going to have for that. So just an introduction today. Let's see what we have. There we go. So just a reminder, it's old pre-calc stuff, but if we've got two functions, we can form a number of new functions a variety of ways. You can have the sum of two functions, the difference creates a new function, the product, sometimes we have the dot there, sometimes we just write them next to each other, and a quotient. So you've got those four with the four kind of standard operations, arithmetic operations that we know. And previously we've looked at rules for computing the derivatives of these functions. So we had the sum rule, difference rule. Everything was pretty clear with those. Product rule and quotient rule are a little bit more complicated. So there's one additional operation on functions that we don't have in numbers, but we want to look at that now, and that's composition. So we're going to look at the differentiation rule for composite functions, or if you have a composition of two functions. And that is called the chain rule. That's the title of this these slides, this video, if you like. So we use a chain rule when the function that we want to differentiate is the composition of two functions, or is a composite function. So for example, if you got something like, say this guy right here, nothing real tricky there, pretty basic function. It's got a little bit to it, so you got the square root of 3x minus 5 is the rule. You could view that as a composition of this function, we'll call it g, which is the root function, and this function h, which is that linear function 3x minus 5 for your output there. So then you can think of f of x as a composition of g with h. I've color-coded it here just so we can see with our first example kind of how things are working. So the chain rule, what that tells you is if you've got two differentiable functions that are kind of building up your function in question, that's a composition. The derivative of f composed with g, so just as a reminder, f composed with g is the rule, the way we compute it, is we think of f of g of x, we sometimes say. We think of g of x as the input for the outer f function. So that derivative, and this is going to be with respect to x, is the derivative of the function f treating g like a variable times the derivative of g with respect to x. So this is a case where the Leibniz notation is kind of clarifying in the way that maybe it gets lost with this prime notation. So the rate of change of, so we said y is f of u and u is g of x. We want to see how does y change with respect to x, not u with respect to x, but how does y change with respect to x? So dy dx is the product dy du, the rate of change of y with respect to u, times the rate of change of u with respect to x. So that's what the rule tells us. Now the rule is pretty simple to state, but we're going to understand it and feel better about it with some practice when you get the hang of it. That's how you'll get the hang of it. Kind of informally, and I think I've used this language already, but you can think of the derivative of the outer function treating the inner function as a variable times the derivative of the inner function. You can think of that as the chain rule. So inner and outer, just like with product, you might think left or right or first or second, or with the quotient rule, upper function, lower function. Or with the chain rule, you think with that composition, you think inner function and outer function. So for example, we got something like this: y equals quantity 4x minus 1 squared, and you want to differentiate that. Now, really want to emphasize, this is not correct, okay? But if you didn't know what you were doing, and you're just trying to do something, you might think, use the power rule, you get that power 2 there, and you might just do the power rule and think you're done. Say 2 comes down, got a 1 left over, I'm good. However, if you expand this, take this, multiply 4x minus 1 times 4x minus 1, you get 16x squared minus 8x plus 1. And that derivative is dy dx equals 32x minus 8. And we know that's true. So that means we must have something wrong with that first attempt. This one here, this is bad, this one's wrong. Okay, so we're actually going to try to use the chain rule and do it correctly. So we're thinking of, like we said, outer and inner functions, non-technical term. For that function in question, y equals 4x minus 1 squared. The outer function is a square function, and the inner function is that linear function defined using 4x minus 1. So if we want, we can think of it as kind of two parts. We can think of the outer function as y equals u squared, and the inner function as u equals 4x minus 1. And now if we think of it that way, y equals that as a function of x, y equals u squared as a function of u, and so the rate of change of y with respect to x is dy du, which is 2u, that's good, times du dx. Now u equals 4x minus 1, so du dx is just 4, that's where that 4 comes from. So 2u times 4, u is 4x minus 1, 4 times 2, 8, 8 times 4, 32x, 8 times 1, 8. And we know that that's the answer. Okay, so a couple examples now to wrap this up, and I'm not going to write all these out. I've got another video where I'll do the examples. What I just want to do here is just kind of walk you through some typed up solutions. So suppose we want to compute the derivative of f of x. It's this, it's viewed as a composite. I've got a third degree polynomial raised to the 5th power. Now one thing we could do is say I can think of it as a product of 5 of those terms and multiply everything out. This is a lot of work, not much payoff. We'll call it a bad idea. So instead I want to use the chain rule. I want to see this as an outer function, which would be the raising the power, that power function. The inner function is that third degree polynomial. So that's what I've got here. And call this one the inner function, and that power function raising it to the 5th power is the outer. Again, not a technical term, but useful way of thinking about it. So what this says is I take the outer function, differentiate that, just treating this like a variable. So say that's the power rule. 5 comes down right here. The new exponent is 5 minus 1, which is 4. We're good there. And then now we multiply it by the derivative of the inside. That's that second part of the chain rule. If I roll back here, it corresponds to this part of it. Or if we like, in the definition, way back when, this part of it, the g prime of x. So let's get caught up. Oh, there we go. So the derivative of that inner function, highlighted in red here, is 3x squared plus 8 minus 0. So 3x squared plus 8. This last line I've just retyped it without the color, and that's good. We're done there. Perfect. For something like this, now you can't multiply everything out, whatever that means. Well, what I mean here is when we had it to the 5th power, we could just take 5 copies of it and just multiply everything out. It doesn't work that way with the root. So there's no long way of doing it, which would be very painful, but would give you an answer. The only possibility is the chain rule. By the way, if we jump back here, If we had expanded this like we kind of suggested, and then taken the derivative, it would have been a polynomial. It would have been pretty big, but we know how to do that. But then f prime would have been super messy and big and not fun. So by keeping this kind of compact and tight together, it makes that result pretty manageable. Okay, so we can't multiply everything out. Got to do the chain rule. And it's actually pretty quick, especially once you get the hang of it. But the first thing I'm going to do is rewrite this from the root notation to see it as an exponent. It's 3x squared minus 4 raised to the 1/2 power. So I use the power rule on the outside function. 1/2 comes down. 1/2 minus 1 gives me the negative 1/2 there, times the derivative of the outer function. Again, not technical, not a technical term. And derivative of 3x squared minus 4 is just 6x. So putting them together, the 6 divided by 2 will call it a 3. Negative exponent just goes down in the denominator. And, not bad at all. Not too bad. The last thing to mention real quick is we get an extra rule out of this from the chain rule. So we previously have shown and used and all that stuff, the derivative of e to the x is e to the x. And we say, well, what if we have an exponential function, but it's not the natural base e? Something like f of x equals 2 to the x, perfectly reasonable. One thing I'm going to note is that, with b being positive and not equal to 1, because that's what we're assuming when we're looking at these exponential functions, it needs to be positive, and if it's 1, it's just a constant function, kind of boring. So you could think of b to the x as e to the natural log of b times x. That's a little bit crazy way to think about it, except when you see it like this, now you can use the chain rule. And so you could say the derivative of b to the x is the same as the derivative of e to the natural log of b times x, which is, well, the derivative of the outside function is itself e to the natural log of b times x times the derivative of the inside function of the composition, which would be a linear function, natural log of b times x. Derivative of that is just natural log of b. And so that equals natural log of b times this, which is a crazy way of writing b to the x. So just kind of sketched out for you real quick what the rule is. Here we've got a nice clean version. So for just kind of a general exponential function, base b, where b is positive and not 1, we've got this rule. So this is another one we can add to the differentiation toolbox. So as long as you know it for the natural exponential function and you know the chain rule, pick up this extra one. So again, the big idea that we're looking at is the chain rule. We want to get a lot of practice with that, and you get a better grasp on it with some practice. But there's not much else to tell you. We've seen the rule, we've seen a couple examples, so in an upcoming video we'll just do some more examples, try to make all the ideas clear.